Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 2. This is lecture 2 and the topic is evaporation. And this lecture we are going to cover measurement of evaporation and also determination of evaporation from water bodies. Now, if you remember, in the previous class we started with abstraction. We talked about various kinds of abstractions, and we also defined evaporation as the process whereby liquid water is converted to water vapor by transfer of water molecules to the atmosphere. We also saw various processes or factors that affect evaporation, and one major being the Dalton's law of evaporation, where the saturated vapor pressure and air vapor pressure they govern the rate at which evaporation takes place. And we also discussed that bulk of this abstraction takes place during the time between runoff events, which is usually long. And we also discussed that there are two kinds of models that are event based models and continuous models. So, if it is a event based model, because that only talks about a particular rainfall event, and we said that during a particular event evaporation is also almost negligible. That is why most of the event based models, they do not consider evaporation as a component. But when we talk about continuous model which run for a long period of time, they do consider evaporation and evapotranspiration, because we already have said that bulk of this abstraction takes place between the rainfall runoff events actually. So, that is where it becomes very important. Coming to measurement of evaporation, typically evaporation is measured by equipment called evaporimeter, and there are various types of evaporimeters available. Few common ones are Class A evaporation pan, ISI standard pan, Colorado sunken pan, and USGS floating pan, and some of which we are going to discuss now. Coming to Class A evaporation pan, this is a pan made of unpainted galvanized iron sheet, GI sheet, and this is how it looks. You can see that is a cylindrical in shape, and this is how it looks. So, it has a diameter of 1210 millimeters and a depth of 255 millimeters. So, that is a standard one has to adopt while fabricating a Class A evaporation pan. That is, its diameter has to be kept equal to 1.21 meters, and its depth is 255 millimeters. Typically, while installing this evaporimeter, it is typically placed on a wooden platform of height 150 millimeters above ground level to allow free air circulation below the pan. So, as you can see here, this is the wooden platform which is used to keep this or to install this particular Class evaporation pan, and this height of this platform is 150 millimeters. And the idea is that there should be free air circulation not only from the top, but also to the bottom of this, so that environmental conditions are maintained, natural environmental conditions are maintained while measuring the evaporation using this pan. And what happens is that for measuring evaporation loss, about 180 to 200 millimeter depth of water is maintained in the pan. So, what we do is that we fill this around 200 mm of level of water, we fill in this evaporation pan, and then a hook gauge is used to measure the evaporation depth. So, what happens that we fill the pan up to a depth of 200 millimeters, and next day morning at 8:30 a.m. Remember, while discussing the non-recording rain gauge, I mentioned that 8:30 a.m. is the time that is typically used by IMD, or it is recommended by IMD for recording all kinds of non-recording meteorological events. And because these rain gauges or the evaporimeters or such kind of equipment, hydrometeorological equipment, they are put in at a single place in a hydrometeorological laboratory. So, that is where the person goes, and then using the hook gauge, he measures the level of water, and the loss of water, that is if it is 200 meter we fill 200 millimeter which we filled, and obviously with evaporation loss the level will come down. So, that will tell us how much water has evaporated, and then water is refilled to this level 200 millimeter level, and then recording takes place in the next day. So, this is how we measure the evaporation using this class A evaporation pan. And when we make the recording at 8:30 a.m., that is the value recorded for evaporation value for the previous 24 hours, as in the case of non-recording rain gauge. The next evaporimeter which is very popularly used is ISI standard pan. It is an Indian version. It is basically a modified version of class A evaporation pan, just now we discussed, and basically that simply means the dimensions etc. That means the diameter is 1.21 meters, the depth is 255 millimeters, all those things are kept the same. Only this pan is made of 0.9 mm thick copper sheet instead of galvanized iron. In this case, we use a copper sheet to fabricate that, and it is tinned inside and painted white outside. So, in order to minimize the losses because of the heat, in environmental heat, it is painted white from outside. So, this is the major change. Another important change is that the top of the pan is covered with an hexagonal wire net of galvanized iron to protect water in the pan from birds and animals. So, if you remember, in case of US class A pan, that is open from top. So, that means the birds or animals, especially birds in any case, and also because it is enclosure, but still the rats or squirrels which are there in the field, they can come and drink water. So, obviously, once birds and animals drink water, obviously that loss will also be counted as evaporation loss, which is not the true reflection of evaporation, environmental evaporation. So, that is why when we cover this evaporation pan with this wire net, that loss is protected, and then we are likely to get a true representative value of evaporation. So, it is a Indian version of class A evaporation pan. The material is changed. Instead of galvanized iron sheet, we use thick copper sheet which is thin inside and painted white outside, and also it is covered with a hexagonal wire net of galvanized iron to protect it from birds and animals. And as a result, evaporation from this pan is about 14% lower than the uncovered pan. So, I mean, automatically because of this covering, we find that we get the evaporation value which we get from this particular type of ISI pan, that is 14% lower than the uncovered pan, that is class A evaporation pan, which we discussed earlier. So, this galvanized iron hexagonal wire net which is used to cover, that definitely helps giving a better representative value of evaporation. The third important type of evaporimeter is Colorado sunken pan, and a major difference is that the previous two we saw, they were circular, but this is a square pan. So, it is a 920 millimeter square pan made of unpainted galvanized iron sheet, 460 millimeters deep, and sunk into the ground within 100 millimeters of the top. So, it is a basically square, as you can see, 920 is the size of the side, and its depth is 460 millimeters. The important thing is that around 360 millimeters of this is buried or sunk inside the ground, and because it is sunk inside the ground, that is why the name sunken pan. So, there is a region behind this name of sunken pan, because this is sunk in the ground. And the main advantage of this pan lies in the fact that its aerodynamic and radiation characteristics are similar to that of lake. So, obviously, as we know that from the factors affecting, we have seen that it is the wind as well as the temperature, both air and water, that affects evaporation of a place. So, obviously, this because it is buried in the ground, so obviously that helps maintaining aerodynamic and radiation characteristics. So, in this case, what happens then, we fill water up to a level of 50 to 75 millimeters from rim, and then there is a stilling well which is which can be used for measuring the water level. So, that means changes in the water level or the evaporation loss, that is how it is basically maintained. Now, we come to pan coefficient. So, basically evaporation pans we discussed just now, they are not exact models of large reservoirs or water bodies. As we can visualize, the large water bodies have different shape, size and look compared to evaporation pan, which is either circular or rectangular, just now we saw. So, evaporation from a pan depends to some extent on its size. For example, evaporation from a pan of about 3 meter in diameter is almost the same as that from a large lake. So, evaporation from pan depends on its size, and experimentally it has been seen that if the size of the pan is kept equal to 3 meters in diameter, then probably it will give you a similar value of evapotranspiration age from a large water body or lake. But as you saw that the recommended value which we use is only 1.21 meters. So, which is only almost a 1/3. So, that is why we do not get the representative value. Moreover, the height of the rim in an evaporation pan affects wind action over the water surface in the pan. Now, if remember, we saw that if you talk about the class A pan, then it had a depth of around 200 mm, and we filled the water up to 200 mm. So, that means the water level even in the beginning was 55 millimeters below the rim of the pan. So, obviously, as you can visualize that if it is a open water surface or large water body, then wind will be moving just touching the water plane. But in this case, because of the rim, there is a gap between the wind movement and the water level. So, that height of the rim also affects the pan evaporation value. Also, the heat transfer characteristics of the pan material are different from those of the natural water body. We saw that we either use a GI sheet or a copper metal or tin coated copper. So, some kind of metal we use for fabricating these evaporimeters. So, obviously, their heat transfer characteristic will be definitely different than a natural water body. So, that also affects the evaporation value which we get. Hence, evaporation measured from a pan has to be corrected to get the evaporation from a large lake under identical climatic and exposure conditions. So, basically, that what that it means is that typically pan evaporation or the evaporation measured from a evaporimeter is slightly higher than what we get in the normal conditions or from a typical large water body. So, that is why a pan coefficient is used to correct the evaporation measured from a pan. So, basically lake evaporation is pan evaporation times a pan coefficient, which is Cp. So, we multiply the pan evaporation with pan coefficient in order to get the representative lake evaporation. So, this table gives the pan coefficient for different types of pans. So, for example, class A pan, if you take, the range is 0.6 to 0.8 and its average value is 0.7. So, that means whatever data which we measure in a class A pan, that on average that has to be multiplied with 0.7 or 70% of that is the representative value of lake evaporation. Similarly, for Colorado sunken pan, the range of coefficient is 0.75 to 0.88 and average value is 7.8. For USGS floating pan, it is 0.7 to 0.82 and the average value of 80. So, depending upon what type of pan you are using, you have to correct your pan measured evaporation value in order to get the representative evaporation value. Let's take an example, and for monthly pan evaporation data near Chilika Lake in 2023 is tabulated below. At the beginning of January, the water spread area in the lake was 1165 square kilometers, while at the end of December, the water spread area shrank to 906 square kilometers. Calculate the volume of evaporation water loss assuming a pan coefficient of 0.75. So, here different months of the year, January to December, pan evaporation values are given, which range from 181 in January to 175 in December, and of course, as you can expect, the highest value in summer, that is May, 275 mm. So, coming to solution. So, at the beginning of January, we have been given the water spread area is 1165 square kilometers, and the end of December, the water spread area is 906 square kilometers. So, basically we use an average water spread area of the lake, and for that we use the trapezoidal formula. So, we know A1, A2. So, using the trapezoidal formula, we can find out the average water spread area. So, in this case, if you put the value of A1 and A2, which is 1165 and 906, we get an average value of the lake is 1032.79 square kilometers. And total pan evaporation loss during the year, or EPAN, is obviously the sum of evaporation values which are measured over 12 months. Remember, in the table we have been given the value right from January to December, and we also saw that the value was highest in month of May. So, we have to sum those values, and that comes out to be 2410 millimeters. And the pan coefficient value is also given to us, that is 0.75. So, the total volume of water loss by evaporation from the lake can be calculated by this simple formula. You remember, EPAN times Cp will give us the evaporation value in evaporation value in depth, and then if you multiply with the average area of the lake, we will get the total water loss. So, that is what we are doing here. EPAN value is 2410 millimeters. So, for unit we put everything in meters, and that is why it is written here 2410 into 10 power minus 3. Pan coefficient value is 0.75, and total square kilometers also we have to calculate in square meters. So, that is why we are multiplying the obtained value by 10 to the power 6. So, that the total volume we get in meter cube, and that is what we get 1866.77 into 10 to the power 6 meter cube, or we can write 1866.77 million meter cube. So, the volume of evaporation water loss from Chilika Lake in 2023 is 1866.77 million cubic meters. That is the answer of this particular question. Now, let us go into determining the water body. Now, up till now we are talking about the measurement. Now, we have also indirect ways of determining the evaporation from water surfaces, and that is what we get into. So, let us talk about that. So, evaporation from water surfaces can be determined in different ways. That is why using water budget or energy budget, or using empirical evaporation formulae, and we will see a few of them here. Now, coming to water budget, the water budget equation for estimating evaporation, which was given by Horton in 1943, can be written as E, that is evaporation, is I, which is inflow, P, which is precipitation, O, which is outflow, OS, which is seepage, and delta S is change in storage. That means, we saw that for finding out different abstractions, we can write this equation in different form. This for evaporation, this is the form given by Horton in 1943. Now, in this equation, inflow, outflow, precipitation and change in storage can be measured reasonably accurately. However, seepage OS cannot be measured or evaluated directly and accurately, and the extent to which this quantity is accurate will affect the true value of evaporation. So, basically as you can see that it clearly says that out of 4 variables we can determine effectively, but OS we have to depend on indirect methods, and if we can do it properly, if we can estimate this value or determine this value effectively, then we can get a reasonably good estimation of evaporation using the water budget equation. This water budget method of determining long time evaporation can be used as a standard for comparing other methods, because though this method is not perfect, it gives satisfactory values for practical purposes, because this equation gives a practically useful value of pan evaporation for long term evaporation. So, that is why many times we may use this water budget method as a standard for comparing evaporation that has been found by using other methods. We saw that we have different other methods of determining evaporation. So, water budget method we can use as a reference point for determining evaporation. Now, let us take an example. A 100-hectare reservoir receives 2500 millimeter of rainfall during a period of 2 years. During this period, the mean inflow to the stream is 1 cubic meter per second. The mean outflow from the stream is 0.8 cubic meter per second, and the increase in storage is 500 hectare meters. Assuming that there is no seepage loss, calculate the total evaporation during the period in millimeters, and this question was asked in GATE 2011 examination. So, coming to solution, different things which are given to us, like rainfall is given as 2500 millimeters. Area of the reservoir is given in 100 hectares, so which is we can write 1 million square meter. Total volume of rainfall, because it falls on the reservoir area, so P times A, that comes out to be 2.5 million cubic meter. The total time given is 2 years. So, that means we can convert that into seconds, which comes out to be 63.072 million seconds. The total inflow volume is given as 1 cubic meter per second. So, obviously, in order to get into volumetric terms, we have to multiply with the time in seconds. So, total inflow comes out to be 63.072 million cubic meter. Total outflow is 0.8 million cubic meter per second. So, obviously, that has to be also multiplied with time 2 years or 63.072 million seconds. So, this value comes out to be 50.4576 million cubic meter, and change in storage is given at 500 hectare meters. So, again we have to convert the units, proper units in meters. So, that comes out to be 5 million cubic meter, and seepage loss value is mentioned as 0. So, that is most complicated component is set as 0. So, from water budget equation we know equals to I plus P minus O minus OS minus delta S. We know all values of, we know the values of I, P, O, OS is 0 and delta S. So, putting that values, we can get the value of E as 10.1144 million cubic meter, that is the total volume, but we have been asked to answer in millimeters. So, that is why the total evaporation depth during the period. So, we have to multiply the total evaporation volume by the area, and then we get a value of 10.1144 meters or 10,114.4 millimeters. So, the total evaporation from the reservoir during the 2 years period is 10,114.4 mm. That is the answer of this question. So, it is a very simple question based on water balance equation. Now, we come to empirical formulae, and the first formula which we discuss is Mayer's formula, which was given in 1915. So, according to Mayer's formula, EL is Km times EW minus EA times 1 plus U9 by 16, where EL is the lake evaporation in millimeter per day. EW and EA are saturated and actual water vapor pressure in millimeters of mercury. U9 is mean wind velocity at 9 meter height, and Km is a coefficient which accounts for various other factors, and its value is recommended as 0.36 for large deep waters and 0.5 for small shallow water. So, depending upon what kind of a water body you are dealing with, you have to change the coefficient. The other before going to the other formulae, like here we have also empirical relationships for estimating EW, that is the saturated vapor pressure. Now, saturated vapor pressure in millimeters of Hg can be obtained by using this relationship, which is a function of T. T is the water temperature in degree C. So, if you know the water temperature, you can find out the value of EA, and also EW, and we also know that relative humidity is EA by EW. So, once we know EW, and if you have a measured value of relative humidity, we can find out the actual vapor pressure also. Similarly, for wind velocity at any height h can be found out using this relationship. UH is equal to CH to the power 1.1 by 7, where UH is wind velocity in kilometer per hour at a height h meter above the ground, and C is a constant. So, using this relationship, once you know the C, we can find out wind velocity at any given height. Now, another important formula which is used for finding out evaporation is Rover's formula, which was given in 1931. According to this, EL is a function of course, EW and EA are there. Here P0 is a new term, which is the mean barometric pressure in millimeter of Hg or millimeter of mercury, and U0 is the mean wind velocity at 0.6 meter height. In Meyer's formula, the wind velocity at 9 meters height is used. In this case, it is at 0.6 meter height, that is very close to the ground is used. Let us take an example here. Estimate the mean monthly and annual evaporation from a small and shallow lake using the Meyer's formula. The relevant monthly data are given below. So, here different months, January to December, we have been given temperature in degree C, relative humidity value is given in percent, and wind velocity at 2 meters above the ground is given in kilometers per hour. So, different months, the velocity is also given. So, obviously, for finding out, we have to find out the monthly as well as the annual evaporation. So, we have to calculate first for all months, and then we can sum up to get the annual evaporation also from the water body. And remember, it is a small and shallow lake, and if you remember, the coefficient value is changed from a small and shallow to a large and deep lake. So, evaporation, let us say we talk about evaporation calculation for January months. So, Meyer's formula we know is EL is given in this form. So, obviously, first thing we have to calculate is EW and EA. So, EW is related to T. Already we saw this is a relationship which relates EW to T, and because we have the temperature given in degree C. So, we can put the values of, say for example, January month temperature is given as 12 degrees C. So, we can put this value and get the value of EW 10.53 millimeters of Hg. Also, we have a relative humidity data provided, that means EA by EW provided. So, once we know EW, we know relative humidity. So, we can also find the value of EA, that is 0.84 times of EW, which comes out to be 8.85 millimeters of mercury. Now, that means this part is taken care of. Other thing which we require is wind velocity at 9 meter height U9, and we also know the relationship that UH at any height h can be calculated, provided we know the value of C. So, now we have been given wind velocity at 2 meters. So, for example, January wind velocity is 5 kilometers per hour at 2 meters height. So, by putting the known value, we can find out the value of this coefficient C, which comes out to be 4.53. Now, for 9 meters, we can again use this relationship by putting the value of C and h equals to 9. So, this value C and 9, and then we get wind velocity at 9 meters is 6.2 kilometer per hour. And also, we know that the Km value recommended for small shallow waters is 0.5. So, that means we know all Km, we know EWEA, we know U9. So, by putting these values, we can find out the lake evaporation comes out to be 1.17 millimeter per day for the month of January. So, similar way we have to calculate evaporation for all other months following the similar procedure, and then we are directly tabulating the value here. So, that means Km value remains the constant. These values were given up to this point, these were given to us this side. So, Km is of course constant. EW already we saw, we can calculate in terms of temperature, which is given for every month. A relative humidity is given, knowing EW and relative humidity we can find out EA, the difference we can find out. Value of C we can determine, because at 2 meters we have been given wind velocity. So, obviously, whenever same value with the C value will same, if the velocity changes, the C value will change. Once we know, we can also get at 9 meter velocity. So, putting all the values in Mayer's formula, we can calculate evaporation millimeter per day for different months, and then also we know the number of days in the month. So, by putting and multiplying that, we can get the monthly evaporation value, which comes out to be. So, for different months, it is January it is 36.27, February it is 47.32, and of course, in the month of May it is highest, is 499.41, and so on. And total evaporation value of course will be sum of this column will be the total annual evaporation, which comes out to be 2251.57 millimeters. And the mean monthly evaporation, that is, if we divide this value by 12, then the mean monthly evaporation comes out to be 187.63 millimeters. So, this is how we can either measure evaporation, or we can determine it either by using water budget method or by empirical formulae, and we can use that, then use that into any other purpose, including in hydrological water balance modeling. And with this, we come to the end of this lecture. Thank you very much. Please give your feedback and also raise your doubts or questions, which can be answered on the forum. Thank you very much.